Hey everyone, welcome back to the 6th episode of the xHCI driver development series. In the last episode, we started covering the runtime register set and set the stage for today's work where we will cover and implement the event ring. This will allow us to receive various events from the controller such as command responses, port connection updates, and other types of event notifications. One quick disclaimer though, if you haven't yet watched the command ring tutorial earlier in the series, please do watch that first as it covers important details about TRBs, which will be heavily mentioned here today. Otherwise, without further ado, let's get right into it. So you may remember from the command ring tutorial that there are two main rings involved in the communication with the controller. You place transfer request blocks or TRBs onto the command ring, and in response get the event TRBs on the event ring. The event ring structure is very similar to that of the command ring as it's essentially a large array of TRBs, with cycle bits being used to differentiate between new and old TRBs. However, sometimes when you have a large number of devices or operations all sending events to your event ring, and you have to allocate a very large chunk of memory for it, it may be a good idea to split up your event ring into multiple segments that are not contiguous in memory in relation to each other. The way to keep track of the segments and tell the controller about them is using an event ring segment table. So let's say each of your segments can hold 256 TRBs. Each of the segment entries is broken down into an address field and a size field. The address would be a physical address of the segment, and the size is measured in how many TRBs can a segment contain. So for each of your segments, you would simply create another entry in the table and fill it with the corresponding segment's physical address and size. Now to my knowledge, at this point in time, a lot of QEMU versions only support using one segment. So in this series, we will only be using one, but that would honestly just make things easier for us. After the event ring segment table is set up, our driver has to initialize and set these interrupter registers that are a part of the interrupter register set that we covered in the last tutorial. First is the event ring segment table size register, which would be set to the number of valid segment entries in the table, so in this case, just one. Next is the event ring segment table base address register, and should be set to the physical address of the segment table. And finally, the event ring DQ pointer register should be set to the physical address of the next available slot in the event ring, as that is the slot that the controller will place the next new event into. Once your driver is notified of the event and is done processing it, it will need to update the ERDP register with the address of the next TRB slot. Similarly, if multiple events arrive at once, after the driver is done processing them, it should advance the DQ pointer accordingly to the next slot after them. It may be a little bit more work to set up compared to the command ring, but it's nothing too complicated, and after you're done, you won't have to come back to it again and change it later. So let's jump into the code and start implementing it. Let's start by opening the xHCI rings.h file, where we previously implemented the command ring. Let's also include the xHCI regs header file since we're going to need it here in a second. The first thing we have to take care of is define a data structure for the event ring segment table entry. The first field is going to be a 64-bit ring segment base address, and that will be then followed by a 32-bit ring segment size field. Keep in mind that in the size field, only the low 16 bits are used. And finally, there is another 32-bit reserved field at the end, which should be initialized to 0. I'm also going to paste in a snippet from the xHCI spec here to remind us of a couple constraints, such as the ring segment size has to be between 16 and 4096 TRBs. Great! Now we can start defining the xHCI event ring class. Let's first define a constructor that will take in a couple of things. It's going to take in the maximum number of TRBs in the event ring, and also the interrupter register set that this ring will belong to. And we'll store those interrupter registers in a private member variable as well. Cool, let's now define the other member variables. First, we need to keep track of how many TRBs our event ring segment has. Then we need the actual buffer where to store the TRBs, and we'll allocate that in the constructor. It would also be a good thing to do to store the physical base of that buffer in a member variable. Next, we'll need a buffer for a segment table, which is essentially just an array of segment entries. And then we'll have an 8-byte DQ pointer, similar to how we had the NQ pointer in the command ring. And finally, we'll need a variable to keep track of our current ring cycle state. Cool. Now I just want to add a few inline getters similar to the ones we have in the command ring, to be able to easily access the event ring virtual and physical bases as well as the ring cycle bit. Great! Let's now go into the xHCI rings CPP file and implement the constructor. The first obvious thing to do is set and initialize the member variables. We're also going to initialize the ring cycle bit to be the same as the initial state for the producer cycle bit in the command ring. That's why we're using the CR0 macro here. Now let's define some size variables. First, the segment count will just be 1, because in this tutorial series we will only be using one segment. The segment size will be in bytes and will be the number of TRBs in the segment multiplied by the TRB size in bytes. Then, the segment table size is going to be the number of segments multiplied by the size of the table entry. Very straightforward. Now we'll allocate the event ring segment block, and for that we'll use our good old alloc xHCI memory function. The size is going to be the segment size in bytes, alignment is going to be 64 bytes, and the boundary requirement for the event ring segment is 64 kilobytes. And now for convenience, we'll calculate and store the physical base address of the segment as well. Awesome! Now that we have the segment memory block, let's allocate the segment table. Again, we'll use the alloc xHCI memory function, and we'll take in the segment table size in bytes, an alignment of 64 bytes, and a boundary of 14 kilobyte page. And now that we have the segment table, let's create our one and only entry for our segment and insert it into the table. The ring segment base address is going to be our segment's physical base, and the segment size will be the number of TRBs in the segment. So be careful, it's in TRBs, not bytes. And finally, we'll zero out the reserved field. Now that we have a valid entry, we can insert it into the first slot in the table. At this point, we can finally use the passed-in interrupter register set to configure its registers. Please be careful at this step, as these registers have to be initialized in this specific order according to the official spec. First, we have to set the event ring segment table size register, and we can set it to 1 since we only have one segment. Then, we have to set the event ring DQ pointer register. Since we'll need to do it again later, we'll abstract it away into its own function in a minute. But after ERDP is written, we have to write the physical address of the event ring segment table into the ERST base address register. Now that we have the appropriate code structure, let's quickly go into our header file and declare the function to update the ERDP register. And now let's replace the to-do comment with the call to it and then define its body below. The implementation is going to be fairly simple. All we have to do is calculate the physical address of the next free TRB slot into which the controller can place a newly generated event TRB. So that will be the segment's physical base plus the DQ pointer multiplied by the size of the TRB in bytes. And that will give you the physical address of the next available TRB slot. And finally, we just have to take that value and write it into the ERDP register. Awesome! At this point, we are done initializing the event ring and the interrupter registers. So now let's go back into our header file and just define some functions to help us with the event ring's runtime management. First, we need a function to tell if the ring has any unprocessed events that we need to look at. And then, let me quickly include my kernel's vector class, because now we need a function to take those new events and dequeue them off the ring into some buffer, which in this case is just my kernel's implementation of the C++ standard library's vector class. It would also be nice to have a function to just flush all the unprocessed events if we need to free up the event ring. And finally, we'll create a private function to dequeue the next unprocessed event off the ring. Alright, let's now go back into our CPP file and first implement the dequeue function, since it's going to be needed by the other ones. The first thing we're going to do here is check if we actually have a new event to dequeue, and if not, we should print an error and return a null pointer. The expectation is that this function should only be called if there is a known new event in the ring. Next, we'll just grab the pointer to the next event using our dequeue pointer. And then we need to advance the dequeue pointer and check for a potential wraparound scenario, in which case the dequeue pointer should be set back to 0 and the ring cycle state should be toggled. Finally, we simply return the dequeue TRB. Cool! Let's now finish up by implementing the remaining public functions. The has unprocessed events function will be very simple and just check if the TRB at the current dequeue pointer matches the current cycle state, which should also match the producer's current cycle state. Now onto the dequeue events function. It will start with a simple loop that will just go through every new unprocessed event, dequeue it, and insert it into the provided TRB vector instance. Now, after all TRBs have been processed and dequeued, this is very important. You must update the ERDP register to now point to the next free slot. And luckily, we already have a function for that, so let's just use it. Finally, the ERDP register will also have an event handler busy bit set, and when the driver is done dequeuing events, it should clear it by writing a 1 to it. Finally, the flush unprocessed events function will be very simple and utilize everything we have just implemented, but just ignore the resulting dequeued TRBs. Great! We're now done with implementing the event ring. Let's go back into our driver's main header file, and next to where we declare the command ring instance, we'll also declare our primary event rings instance. Now, as you may remember, in the last episode, when we configured the runtime registers, we left a to-do comment for the event ring related registers. So all I have to do now here is instantiate the event ring. And now in the constructor, we'll pass in the event ring TRB count, which is 256, and our interrupter register set 0. Then, to make sure everything worked correctly, I'm just going to print out the values of the interrupter registers here to see if the values look good and make sense. And let's now compile the project and see what we get. Awesome! As you can see, the interrupter registers got printed and look like they contain valid physical addresses, and the event ring segment table size is set to 1. This is a huge milestone because we are now done configuring the controller, and in the next video we will write the logic to actually start it back up. This will allow us to receive interrupts, check for various port events, and start communicating with the controller, so tons of exciting stuff is coming. I hope you all enjoyed the video, and please leave a comment if you have any questions. Hope you all have a wonderful day, and I'll see you in the next one.